I am Adhokshit Mishra. Currently, I am working in EY as cybersecurity consultant. My area of interest is in mostly offensive side of malware, as in I mostly work on how to work on new attack vectors, how to bypass various security systems, and so on. And apart from malware, I also dabble into applied cryptography to certain extent. So that is my background. And today we will be talking about anti-reversing, which comes under offensive side of malware, because here we deal with bunch of techniques that basically give us more time by hindering in analysis of the code by a malware analyst. So techniques that hinder with malware, wait, malware analysis. And here again there are basically two types. One is hindering static analysis, and other one is hindering uh, dynamic analysis. Here what we will be covering will be the second point, because first part is mostly about cryptors and packers. Second part is a bit more interesting for me, so this is what we will be covering. So here there are again bunch of techniques. First example is, for example, we can uh, try to detect debugger and related tools to see if we are under a debugger. Then there are techniques which can basically prevent debugging and analysis, as in if a debugger tries to attach to process, either it will fail to attach or it will attach but it will get completely bogus output. And then there are techniques which will detect and prevent patching. Patching is a process of overwriting bunch of memory area in the target process. So there are techniques that help us in detecting whether certain area in memory has been patched, and if it has been patched, there are techniques which we can use to recover the original state of the process. Again, this is not something limited to malware. This is also used by many gadget software as uh, anti-piracy measure. So it is not something strictly limited to malware. Now, when we talk about detecting a debugger, again there are many techniques depending upon how hard we want to go. For example, we can rely on the fact that generally a process will be bit slower under debugger than out of debugger. And the reason being that when a process is being debugged, the analyst will halt at certain places, try to figure out what exactly is going on, then and then try to resume the process. So there will be significant delay that we can compare with some sort of known good value. And if we see that we are spending too much time for some strange region, we can say that okay, we are under some sort of analysis and we can either change the code path or we can exit or we can do something else. Another idea is to process. We can detect if there are analysis tools running in system, or we can detect if our parent process or parent of parent uh, is some sort of unknown process. For example, if I talk about Windows, if we are going to start a binary, most of the time the parent will be your shell. Similarly, in Linux, if you are going to start a process, most of the time the parent process will be your shell. And if you see that there is some strange binary that you are not really that you don't really identify as a shell or as something like systemd or some unknown good process, and we can say that okay, possibly this process has been started by something else and there is a chance that this is going to analyze something. So we can try to change our behavior or simply exit at that point of time. So we will start with first part, this timing one, and the idea is actually very simple. The code samples are in very simple C++. I hope you are comfortable with that language. And the idea is basically this. Here, what we are doing, that we have a loop. This is our actual process that where we want to measure the time. So before getting into the loop, at the entry of the loop, what we do, that we take the timestamp. This is our beginning timestamp, and at end of the loop we do this. We take the end time, and when we take the difference, we get the duration, and the if the duration is more than some known good value, we say that debugging attempt is going on or something like that, and it works like something like this. If I run it without this, it will keep running in the loop, and if I run it under a debugger right here, okay, now I try to see what exactly is going on in the process, trying to figure out if this process is legit or not. And when I decide that okay, it is simply doing some benign stuff, as in something that is not harmless, I let it run, and it says that debugging attempt detected because it has taken way too much time than we originally anticipated. Now here there is a problem, that if this threshold is too tight, you will end up in this state on many legit hardware as well, because there are too many things that are going to interfere with your timing. For example, your process may be put into sleep state, or it may schedule a bit too late, or maybe your system is running slow, or maybe you are running on either slower CPU or a system with pretty low resources or whatever. So this is not really a good idea. So but this one is really simple to implement, and this is something I have seen in a very simple type of malware that try to interfere with analysis. This one is slightly better, where we try to detect the process, and for that, this is the code. And what we do, we simply check if we are under debugger, and this is actually very simple one. We start from here. This is using slash proc file system, and slash proc file system is something that gives us a lot of information about uh, self. So this is a virtual file system, as in it is not really backed by a physical file system somewhere on your hard disk. It is coming directly from a kernel. Now, okay, this is the part of virtual file system that gives us a lot of information about any process. So if I go to slash proc slash shelf, this will show me process related information related to the shell I am currently connected to. So for example, if I want to see what was the command line, I can read this file. It will show me that okay, this was the command line, this is my shell. Similarly, if I do this exe will be pointing to the actual binary that was used to start the process. Similarly, if I read this maps file, it will show me memory map of the process, start address, end address, permission, size, and finally the path of binary that has been loaded. Similarly, it will show that okay, here I have heap, here there are bunch of shared objects that have been loaded, then here I have a stack and bunch of other stuff. Similarly, I can check whatever mount points are actually accessible to this process, so I get this. uh, Similarly, there is something called smaps that will give me even more detailed information about memory layout. So these are bunch of files, and their detailed documentation you can find somewhere on kernel.org. I don't remember the exact path, but it is there. You can refer to that to figure out what exactly is there in what file. And what exactly we are reading here? We are reading this stat file. And as for the documentation, if we read this file and we go to fourth value, so this is first one, this is second, this is third, this is fourth. So this one is PID of parent process. So if I want to check what is the parent process, I can go slash proc slash 1812 slash exe and try to see what it is there. Okay, the parent process is this console, that is my terminal emulator that I am running here. So here what we are doing, we are simply reading this file, we are reading the fourth value out of it. Here we get the parent process, and in parent process we are trying to figure out where this path exactly is pointing to, and then we have these two values where we are going to match with. So if the parent process matches with GDB or LLDB server, that means we are under debugger. And this works like this. Here it prints that I am not being debugged, and if I run it under debugger, it will say I am being debugged. Now the problem with this approach is that I can change the name of process on my system before analyzing it. For example, if I try to run it under S trace or L trace, it won't say that it is getting debugged. So if I do this, it is going to say that it is not being debugged because it is not checking for S trace or something like L trace. So this is another limitation with this approach, and because of this, we move to next technique, and that is basically preventing debugger and debugger like tools. Now, if we want to prevent a debugger before we can do anything, we have to know how a debugger works. And under Linux, there is a syscall called HeatRace. This is a syscall. We call it process trace that provides us all the process tracing and debugging mechanism. So, for example, if I am writing a debugger, or if I am digging into source code of GDB or LLDB or any other debugger on Linux platform for that matter, I am going to see that it is using ptrace call heavily, because this is how we are going to set breakpoints. This is how we are going to read registers. This is how we are going to read the process memory, override the memory, do anything. If we want to do pretty much anything inside address space of another process, or we want to control it, we have to use ptrace syscall. There is only one syscall that we have to deal with, and there is a limitation with ptrace that only one process can ptrace a given process, as in no process can be ptraced by two or more processes at the same time. What does this mean? This means that if I ptrace to my own process, any debugger will not be able to uh, attach. Or if I am not able to ptrace to my own process, something else has attached to me via ptrace. So this is a very simple logic. And here what we do, that on a startup we attach to our own process as ptrace, and we simply try to figure out if we attach successfully or not. So it looks something like this. In beginning I call ptrace call, and if it gives me -1, that is, it was unable to attach. I simply print don't trace me. It is actually that simple. Now, if I try to run this, so it is printing normal execution, and if I do GDB, this says don't trace me. And plus point with this is that I don't have to match with any process. If I do strace, that is also using ptrace by the way, it will say don't trace me. Similarly, it will also say something like that with the L trace as well. Here it says don't trace me. So here I do not have to match with known process, or I don't have to bother with that. Analyst will change the binary name and try to figure out what is going on. I can simply ptrace to myself. Now there is a problem. The problem is that a malware analyst may try to change its uh, return value to fool the process that it has attached to itself. So in that case, what we do, that is the next technique. We retrace our own process multiple times, and we maintain an internal state. If state does not match with known good state, something has interfered with us. And the idea is basically extension of this code, which looks something like this. So here I have a variable, and I am expecting first call to succeed, and the next call will obviously fail because we have attached to ourselves. So if I succeed in attaching to myself, I set it to 2, and if next call fails, I set it to and if by the I just multiply it by 3. So now if nothing has attached, I end up with 6 in this variable. And if something has attached, this particular line will not execute, and I will get 0 into 3 equal to 0. So here if my variable does not match, that means that the process is under analysis by some other tool. And if we complicate this chain, it is possible to make malware analyst a bit cry, because he has to figure out exactly what to return where and how exactly these states are getting maintained. This is very minimal example actually. And now if we run this, it works as expected, and we try to do this, it will say don't trace me. And exactly same is going to happen with tools like strace or trace. Now there is another problem with this, and the problem is malware analyst will take time to figure out internal state. Now it too has a solution, and the solution is actually really simple. Solution basically boils down to this. So malware analyst is going to take some time to figure out our internal state. So what we do, that we rely upon invalid syscalls. And what it does, under normal execution, we trace to own process, intercept syscalls, and invalid syscall is found, fix it by mapping to correct syscall. And what happens under analysis? Under analysis, we cannot intercept syscalls in our process, which leads to invalid syscall, which leads to lost execution. So this is a little bit more complex than this one, but still not too complicated. So it looks something like this. Here we have a custom syscall number that I have defined as 10,000. Here we define some more functions, and this is the main function. Here what I am doing that I am forking. Here we are checking for error condition. If it is less than 0, fork has failed. If it is child process, as in PID is 0 for us, that means we are going to run this tracy function, that is this one. This is where we are going to do it, and if we are parent process, we will call tracer. And here we are going to deal with ptrace. Here in tracy it attaches to itself, and here in parent process we simply wait for the child PID. And here what we do that we check for whether it has stopped. We said that we want to trace syscall. We wait for the process to halt, and then we match the registers and all that stuff, and then we swap the registers for this write syscall. We map it to basically a known good syscall. We set the registers back into the process, and then we continue the execution. So this is how it basically works. And if I try to run it, it will look something like this. And if I try to break it to this one, and if I try to run it here, okay, continue, it will simply go on because GDB did not attach to child process. So let us set to set follow fork mode to child. So it will follow the child. It will drop the parent process and attach to child process. And if we try to run continue, okay, it has stopped somewhere. Wait, it has this an alert and it has stopped somewhere else. This is not something that we this is basically something that we wanted to happen in the under debugger, because our normal execution didn't go through. So again, we can mix all of these together. So once we are done with this, there are some more techniques, and now we basically try to feed bogus data to malware analyst. And the first technique that comes here, this comes detecting breakpoint, and then comes removing breakpoint. So before we try to figure out how to detect the breakpoint, we need to know how a breakpoint basically works. And there are two types of breakpoints. One is software based, and the one is hardware based, using debug registers in CPU. Again, there is a limitation with hardware based. Only a handful debug registers are available, and here we can have as many breakpoints as we want. So most of the time our debugger will be using software based breakpoint. Actually, hardware based are supported, but they are not used by default, because we get only 4 or 6 debug registers that we can actually use, and many times you will be dealing with many more breakpoints like 10, 20, 100 or something like that. So software based breakpoint is default, and how it works that basically setting a breakpoint. Now suppose my original code looks something like this: C3 0x90 0x9 something like this. This is my original code, for example, and I want to set breakpoint here. So what will debugger do? That it will change its first byte. This one, it will change it to 0xcc. It for breakpoint we are using 0xcc. That is basically interrupt third. This is how it is implemented on most of the operating systems, including Windows and Linux both. And this is kept as single byte instruction because we may need to put breakpoint on single byte instructions as well. So we do not want to spill over other nearby instructions. Modified code will look something like this: 0xc9, 0xc3, 0xcc, 0x43, 0x90, and here 0x9 is backed up somewhere else. Now when process starts executing, it continues here, it hits on this one, it raises this interrupt. This interrupt is captured by the debugger. Debugger again overwrites this instruction with 0xc9, that was the original byte, and it will let you analyze the state or to figure out. And when you move on to next instruction, the debugger will again overwrite it with 0xcc and back up the original byte unless you remove the breakpoint. So this is how software-based breakpoint works, and this also gives us an idea on how to detect and basically remove it. So what we need to do, that we have to check whether we are seeing 0xcc as first byte in our instruction, in any of our instructions. And if we are going to see 0xcc, we can say that okay, we are under some sort of debugger because some sort of breakpoint has been set in our code. And once we know, we may try to change the behavior, or we may try to remove this breakpoint by overwriting this byte here manually, assuming we have a backup of all the first bytes of all the instructions that we are going to run in the memory. So the breakpoint part looks something like this. Here what I am doing, this is a first case where we are being very lazy and we are only checking first instruction if it is 0xcc. So this is the main function. Here we take a pointer to this particular function using function pointers. We check if the first instruction is 0xcc, and if it is so, we will say that we are under debugger, because we are somehow relying on the fact that malware analyst will use that break command under debugger. But let us try to see what exactly happens if we do this. Now we try to gdb-q. Disassemble secret, and we want to set breakpoint here. And if we try to continue, it will say breakpoint detected. Now I used this command instead of doing break secret. There is a region, and region is basically this. If I do this, here it set the breakpoint on line 14, that is the very beginning of the function. And if I am using break secret using function name, it is setting on line 15, which is this, and that means that it is not going to set breakpoint at very beginning of the instruction. And if I try to run it, it has hit the breakpoint. We didn't get to detect it because this particular check failed because the first byte is not 0xcc. So we improve this. We cannot be lazy everywhere. So what we do that we maintain an offset of all the first bytes of instructions in our code, and then we try to match if there is 0xcc on any of the bytes. Why are we maintaining an offset? Because we do not want to uh, deal with the case where 0xcc is in one of the operands. That may be the legitimate case. We do not want to get into some other state saying that okay, no, we are under debugger for some reason. So we want to avoid that. That is why we are maintaining this initial offset. And how exactly I get the initial offset? I get the initial offset using this. In GDB output, here in angle brackets, we are getting the offset. I simply copied this into my code. So this is how I got the offset. And now if we test this, it says try breakpoint and secret. Good enough. We try to attach a debugger. We break at this function and we try to run it. And it says that breakpoint has been detected. That was the intended output. So here our code is basically working. We are able to set, we can set breakpoint in anywhere in the given function and we will still be able to detect it. Now the third case. And third case is basically removing the breakpoint. Here we are going to remove this with the original byte. And how we are going to do that? We are basically maintaining the offset as well as original bytes. The bytes I got from obj.utility. So here I check for breakpoint, and if there is a breakpoint, I run this code. And here for this, I need to make the memory page where my code is stored. I need to make it writable. And now, unlike Windows, where we can set permission anywhere on any size buffer, this is not how things happen in Linux. In Linux, we need to change memory permission at page level. So the start address must be starting of the page, and the total size here I want to set the permission should be integral multiple of page size. So for that, what we do basically, we first get page size using this function, and then we try to figure out start address of the page where this function is stored. Now here you need to do something that I have not done for sake of brevity, and this is here. Setting memory permission. Now what I have done that I have assumed that my whole code is only in one page, because if I do this here I have set memory permission for only one page because I am assuming that my code will be in only one page, and this is going to be true because my function is uh, ridiculously small. There are only I think 70 or 80 bytes only, but this is not necessarily true in practice. So if your function goes longer, or maybe your function is split between two different pages, so you need to figure out exactly how many pages you have to deal with. So the idea is this: we have this starting pointer, start of function, and we have this is end of function. So our scheme should be something like this. It get starting address of page for page where function begins. Get starting address of page where function ends. And then you need to figure out how many what is the offset between these two, and then you have to set, okay, let me call it suppose this is uh, start page. So suppose I store the addresses in these variables. So now how much is the size of buffer where I need to set memory permission is basically this. So I take this and so this is going to give me offset between start and end, and then here we need to add page size because we have only taken starting address of the page. We need to change up to end of the page. So this will basically set memory permission on all the pages where your function is stored. So if it is spelled across two pages, you will be setting new permission on two pages. If it is using 5 pages, you will be setting permission on 5 pages. For sake of POC, I have not done this much here in the code. So here finally we call this mProtect function. This is the starting address from where we want to set the permission. This is going to be start address of a page. This is a total size that needs to be multiple integral of page size, and here desired permissions that we want to have. So this is read, write, and execute. So we check that it is not really failing, and if it succeeds, we basically match with the original bytes and overwrite it with the original bytes. And this is how it works. I set a breakpoint, I run it. It says breakpoint detected and breakpoint removed. My debugger did not halt at the breakpoint because it was removed before the control reached at that particular phase, that particular instruction in the memory. So this is how this works. And now we are left with last topic of today's session, and that is patching detection. Detecting patching on process. And idea is similar to breakpoint detection and removal. So what we do that for detecting there are a bunch of techniques. First one is we can either have complete copy of code somewhere else as well and try to check if any bytes are changed, or we can do checksum validation of our code. If checksum fails, that means code has been bashed. So the first idea is actually really simple. here we have copied all the machine code, and here is in we have this function is function patch, and here we simply start from the function and copy of machine code, and then we simply whether all bytes match or not. If somewhere there is a mismatch, we say that function has been patched, and it works like this. So we have this disassembly. We try to overwrite it. C9. Oh, okay, wait. 0x C3 here and C9 here, and then we disassemble secret again. Here we have changed the order of instruction. So if we try to run, it basically watches up somewhere else. Actually, it should simply say that function has been patched, but it is crashing instead. This is something that I have to figure out, but there is another code that is going to work, and this is this one. Here we are simply checking for checksum. So here this is the function pointer, total size, and checksum. I have already calculated the checksum to be this, and this checksum is basically CRC32 that is calculated on runtime as well. So this is basically this. Here we calculate the checksum again, and then we check if those checksums match or not. Secret. Okay. Now we try to run it. Okay, it too is crashing. I think there is something change in compiler. It simply received signal this segmentation fault. If I try to run this one, okay, and if I do this, done. This is under secret, and I try to override here. Okay, this too is crashing for some reason. This is something I have to figure out now, and that too basically live. Okay, let us see why exactly this started failing, because last time I wrote the code, it was using some different compiler that basically changed. Okay, let's see. Name. This function patched. Continue. Okay, it has this here. This is symbol secret, and now I try to change this. change this to 0x90 and I disassemble secret again. Okay, it has changed and we try to continue. Okay, it says function has been passed as it should. So okay, at least this one is working slightly differently. Similarly, if we go to second one, like is function passed, run, then we disassemble secret. We try to change the bytes again, 0x c9, here we do 0x90, we confirm that it has changed. Okay, and we try to run it, and this one is actually failing for some reason. Okay, first one was basically working, and then we try to check the third one. First, continue, disassemble secret. Okay, and continue. Okay, this too is crashing. Okay, this seems that something changed in GCC 10, that is crashing the code somewhere in memory, because after changing this shouldn't be appearing anywhere, but this is appearing apparently. That means compiler has changed something that I have to figure out, but basic idea is basically this one. So this was the first one where we matched all the bytes. This is where we are matching the checksum, and this is where we are basically using the same idea, and then we are trying to unpatch the function to restore it. And here what we are using, that we are simply setting the page size again to, we are setting the memory permission again to read write execute, and we are simply overwriting all the machine codes. And if you are going to try these codes, ensure that you are using GCC 9 point something, because I just changed my compiler to GCC 10 and it has changed something in the generated code that it is not working right now, so I have to figure that out. In meantime, if I am able to fix it for GCC 10, possibly I will share updated code as well, but right now this code is going to work with GCC 9 only as of now. Okay, so this basically covers all the topics. So does